We're back. 16.5. Working with conditional probability. Hopefully you love tree diagrams. You love conditional probability because that's what this section's all about. Let's dive right in. First, let's start us out. Let's remind ourselves of this conditional probability formula. Reminder that this part over here on the left, that means A given B. And here's how we calculate it. That numerator, sometimes also written as that A intersection B. So we're going to be using this formula extensively in this section. It is the conditional probability formula. Very important to know and love. But we've already gone over that, so just want to display it up here, and then we can kind of jump right into the examples. All right, during a flu epidemic, kind of hitting a little too close to home here. 35% of the school students have the flu. Of those with the flu, 90% have a fever. Fever is also possible for people without the flu. School's nurse estimates that 12% of those without the flu have a fever. All right, I'm going to start us out here by just making a tree diagram to describe the situation before I try and calculate really any probabilities. All right. So kind of my first break in the branches here is going to be people either have the flu or people do not have the flu. And then the second kind of branch break is for if you have the flu, you can have a fever. If you have the flu, you could not have a fever. And the same branch break over here for the no flu. We'll have fever and no fever. All right, so let's start throwing the probabilities in here that are just given up here. So 35% of students have the flu, so I will put this over here as 0.35. All right, I've seen a lot of you guys try and really force fractions into the equation. Decimals here are totally fine. I mean, they're actually going to be easier to work with. I know I'm usually anti-fraction guy, but we're going to be, usually anti-decimal guy, but we're going to be just throwing things into the calculator here. So it's not really that big a deal. It'll probably make things a little bit easier to work with. All right, so for the no flu over here, it does not actually give us a number, but we know every break in the branch in a tree diagram needs to add up to 1. So to figure out the no flu portion, all we have to do is 1 minus 0.35, which is just 0.65. All right, so of those with the flu, 90% have a fever. So in the flu break down to the fever, that's going to be 0.9. No fever will be 0.1. By the same logic above, every break in the branches needs to add up to 1. And then the school's nurse estimates that 12% of those without the flu have a fever. All right, so this would be 0.12. This would be 0.88. So there's our tree diagram. It's going to be very useful. So let's move on to part B. So we want to find the probability if we select a random student, what's the probability they have a fever? Okay, so basically when you already have the tree diagram, it's pretty straightforward. All you want to do is multiply down the branches of the ones that end in fever and then add up those probabilities. All right, so first we'll have the probability that someone has a flu and the probability they have a fever, 0.35 times 0.9, plus we're multiplying down the other branch that ends in fever. So no flu, 0.65 times fever given no flu, 0.12. Just do some calculating here. And I get 0.393. Beautiful. All right, so move on to that should hopefully be review. Not too bad. The new stuff, here we are in part C. All right, so find the probability of flu given fever. All right, so if you find a randomly selected student here and they have a fever, what's the probability they also have the flu is basically what that's asking. All right, so this is something, and normally in a tree diagram, we kind of just multiply down the branches. Here, what this problem is asking, it's called reversing the conditioning. Okay, we're basically starting off here at the bottom of the tree and trying to work back up. And unfortunately, you cannot just multiply back up the branches. Okay, but what we can do is we can use our conditional probability formula. So we have the probability of flu given fever. All right, I'm just going to kind of fill in the parts from the conditional probability formula. So the numerator is going to be the probability of flu and fever, and the denominator will be the probability of fever. All right, so right away I see that for the denominator there, for the probability of fever, well, we calculated that in part B up here, so that's going to be pretty useful to us. So now we just got to figure out what to do in the numerator here, the probability of flu and fever. Well, given our tree diagram here, that's going to be pretty easy to find. Flu, fever. All right, so what we can do here is our numerator will just be 0.35 times 0.9. That's going to be the probability of flu and fever, just multiplying down the branches, divided by the probability of fever, which we calculated in part A, 0.393. So, just once again, heading to the calculator here. If I throw that in, I get 0.802. Okay, so that means if you have a randomly selected student who has a fever, that's the probability that they also have the flu. Okay, flu given they have a fever. Okay, all we had to do was just head to our conditional probability formula. Okay, fill in kind of the missing parts. In the numerator, we had to do that flu and fever, which we just multiplied down the branch that had both flu and fever. For the denominator, we had to just find the probability of fever, which is just multiplying out the branches and adding the ones that end in fever. Cool, cool. Oh, wow. A 30-part question. I can already hear the groaning from everyone in advance. Oh, but let's do it. It won't be too bad. We have a probability tree here. Just want to kind of get used to some of the notation, what a lot of these symbols mean, kind of get very familiar working with these conditional probabilities and the tree diagrams. So a lot of these we'll be able to get through very quickly. So let's start at the top. Probability of event Y. Well, here's Y right here in the middle. Okay, and we know that every break in the branch, all right, the sum of the probabilities has got to be 1. We already have event X over here is 0.5, Z is 0.3. So that means that event Y, the probability there is going to be 0.2. All right. B given Y. Okay. So we have a lot of B's here, okay? Some of which we already know. But the one we're interested in is for B given Y is this one, okay? That one there, we know that Y has already happened. We're looking for the probability of B, okay? It may look like we're gonna have to do the conditional probability formula here. We're not, because we know every break in the branch needs to add up to 1, All right, so here we know that A is 0.4, so that B is going to have to be 0.6. Just 1 minus 0.4. All right, B given Z, that's over here. You can do the same logic. We already know that A given Z is 0.3, so B given Z is just going to be 0.7. All right, so now we at least have the tree diagram all filled out. Let's move on to some actual probability work here. So that first one, part D, the probability of X and A. Okay, this is actually quite simple. All you got to do is just multiply down the branches, all right, for X and A. So in this case, we know X is 0.5, and we know A given X is 0.2. So 0.5 times 0.2 equals 0.1. All right, for part E, same logic, the probability of Y and A. Well, I know the probability of Y is 0.2, probability of A, 0.4. So 0.2 times 0.4, we would get 0.08. Using that multiplication rule. Okay. Z and A for part F here. Same rule, okay? All we gotta do is just multiply down the branches. So it's gonna be 0.3 times 0.7, which is 0.21. All right, great. So we got all those multiplication rule ones out of the way. Let's do G and H now. So for part G, the probability of A, we're going to have to multiply down all the branches that end in A, and then we're going to need to add all of those outcomes up. So going down X, we'll have 0.5 times 0.2 plus, for Y, we'll have 0.2 times 0.4, and then for Z, we'll have 0.3 times 0.3. So let's just throw that in the calculator just so we can move quickly. And I get 0.27. All right, for H, I'm going to do the exact same thing. Or actually, we can do a little bit of a shortcut here, okay? Because we know A and B are mutually exclusive, so we can actually just make this a little bit easier on ourselves and do the complement rule here. We've already found the probability of A, so we can just do 1 minus the probability of A. And therefore, the probability of B is just going to be 0.73. All right. So I apologize, this slide is getting quite crowded here. These final two. Let's get to some conditional probability work here. So part I, the probability of X given A. Okay, so we're going to use our conditional probability formula, the probability of X and A divided by the probability of A. All right, well, it's fantastic that we've already done most of the work here. We found the probability of X and A in part D. Okay, so that's going to serve as our numerator. And then the probability of A we found here in part G. So that's going to be our denominator. So 0.1 divided by 0.27 is going to be approximately 0.37. All right, and then last one here. Part J, probability of Z given A. Once again, we're going to want to use that conditional probability formula. So the numerator will be Z and A divided by the probability of A. So luckily, we already found Z and A over here in part F, 0.21. The probability of A has not changed. It is going to be, did I screw something up here? Just noticing that I actually screwed up part F here. For Z and A, I use B, so it should be 0.3 times 0.3. Which would be 0.09 actually. Apologize about that, but I caught it before I recorded the video. That's an improvement. So this should be 0.09 divided by the probability of A, which is 0.27, and therefore equals 0.33. All right, awesome. So last one here. We have results of a large study on the reliability of HIV testing suggest that among people with HIV, 99.7% of tests conducted were correctly positive, while for people without HIV, 98.5% of tests were correctly negative. The clinic serving an at-risk population offers free HIV testing, believing that about 15% of the patients may actually carry HIV. What's the probability that a patient testing negative is truly free of HIV? All right, first things first, I'm going to ignore that question completely right now. I'm going to draw my tree diagram, help myself actually visualize what's going on here. So the first break in the action here is going to be they actually have HIV or they do not have HIV. Okay, which the problem says that 0.15, 15% of people have HIV, and for the no HIV, just 1 minus 0.15, which is 0.85. The second break here is they are going to either test positive, test negative for both these cases. Okay, so 99.7% of the tests conducted were correctly positive, so that's going to be our value over here. For test negative, it's just 1 minus that. And then for testing negative here, correctly negative, is 0.985. So this is just 0.015. All right. So now that the tree diagram is filled out, it's going to be very useful to kind of organize our thoughts here to answer the question. So what's the probability that a patient testing negative is truly free of HIV? So I'm going to kind of write this out in conditional probability notation. We're looking for the probability that they do not have HIV given that they tested negative. Okay, so once again, this is another example of reversing the conditioning. All right, we can't multiply back up the branches. We're going to have to use that conditional probability formula. So we're looking for the probability of no HIV and test negative. divided by the probability of testing negative. So the numerator here, for no HIV and test negative, all right, we're just going to be multiplying down the branches there. So that will be 0.85 times 0.985. And the denominator for the probability that they're testing negative, so we need to multiply down the branches and add each one that ends in testing negative. So that's going to be 0.15 times 0.003 plus 0.85 times 0.985. All right, I'm going to throw that in the calculator. Be very careful about your order of operations here. Make sure you enter it if you're entering the whole thing in one foul swoop, make sure you include the necessary parentheses. And I get 0.999. All right, so it's good news. This test works pretty well. If you test negative, there is a 99.9% chance you are truly free of HIV. All right, and that's it. So hope you enjoyed. See you next time.